Welcome back. In this section we'll talk all about sets, and we'll start with a definition. We'll say a set is an unordered collection of objects called elements or members of the set. And then we'll also say a set is said to contain its elements. And further, we write element A is contained in, that's what this kind of rounded looking E thing is, set A. Set A is notated by a capital A. We'll say to denote that element A, written in lowercase, is an element of set A, written in capital. We'll also say the notation A is not in set A means that element A, again in a lowercase, is not an element of set A. It's important to note that all of the sets are indicated in uppercase, so I'll put a note here. Sets are in uppercase. Letters. And elements are in lowercase. And we'll scroll down a little bit. And we basically have two ways of listing sets. We have a roster method, and with the roster method we're going to list all elements of the set. And we'll list those inside of curly braces. So we could do an example, and you could list, say, all vowels. And you could say the set of all vowels, with a capital V, is equal to And then inside of our curly braces, we'll say A, E, I, O, U. And we'll close curly braces. And that would be an example of listing all of the members of a set, or all of the elements of a set, inside of curly braces. And that's a roster method. With the roster method, you can also use ellipses It is your 3 dots when a pattern is obvious. Oops. So we could do an example here, and we could do integers. Again, inside of curly braces, go 1, 2, 3, and then an ellipsis, dot, 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 through 99. And that pattern being obvious, we're increasing by 1 integer each time. The second option for how to do sets, we'll go to a new page here, is going to be to use set builder notation. And set builder notation gives us a little bit different options. This allows us to characterize all elements in the set by stating the property or properties must have to be members. And we can do an example. We'll say set O of all positive integers less than 10 can be written as O is the set, use our curly braces here, of all x such that, that's what our vertical line is, x is in, x is an odd positive integer less than 10. I'll close my curly braces there. And as I was writing that out, I noticed that when I wrote the problem up here, I wrote set O of all positive integers, and that should be all positive odd integers so that that matches. Okay? All right. Similarly, we can write this also as O is the set of all x in z plus, z being the set of integers, plus being positive, such that x is odd and x is less than 10. And then we'll close the set out with the curly brace. So those are two alternative ways of listing the same thing. The second one just being using a predefined set. These are common sets that we have learned throughout math for many, many years. So you're probably already familiar with them. I'll go ahead and write them out as well. So we'll say commonly used sets. We have set n being 0, 1, 2, ... We'll call those natural numbers. Set z being set of integers. We'll start with an ellipse, and we'll go -2, -1, 0, 1, 2, an ellipse. Close that up, and we'll label that integers. We can do z plus being set of positive integers, which would be 1, 2, 3, ... We can do set q such that we've got p over q such that p is an integer, q is an integer, and q is not equal to 0. And that is known as the set of rational numbers. Okay. We can do R, set of real numbers. R plus set of positive real numbers. And C being the set of complex numbers. We also have notation for intervals of real numbers. When a and b are real numbers with a less than b, we write square brackets a comma b to denote the set of all x such that a is less than or equal to x and x is less than or equal to b. Notice the square brackets there denote an less than or equal to sign. You can have a square bracket on one side and a rounded parenthesis on the other side. and that would equal set of all x such that a is less than or equal to x, and x is strictly less than b. And these are similar to other notations that you've seen. You've most likely encountered this before. So we'll go parenthesis a comma b square bracket would be the set of all x such that a is strictly less than x and x is less than or equal to b. And then last combination, where you've got parentheses on both sides, it's going to be the set of all x such that a is less than x and x is less than b, like that. And then we'll do a little note here. And we'll say we've got a comma b inside square brackets is called closed interval. From a to b, and we've got parentheses a comma b. It's called open interval from a to b. All right, so now that we've defined some terms and some methods for determining sets, we can take this concept of a set and say the concept of a set is essentially the concept of a data type. In programming, and in databases. All right, so now we have the idea of a set taken care of. We can also introduce a new definition. This definition will be that two sets are equal if and only if they have the same elements Therefore, if set A and set B are sets, then A and B are equal if and only if for all elements x is in set A if and only if x is in set B. And then we can say, we write set A is equal to set B if A and B are equal sets. And this idea of determining if two sets are equal becomes very important as we move forward. So with anything, when you're trying to prove something, you always have to come back to a definition. So in this case, this is the definition of two sets being equal. In order to show that two sets are equal, we have to show what is in the definition, which is for every element x, if x is in A, then x is also in B. So it's a if and only if there on both of those, and that's what we'll have to determine and have to be able to prove as we move forward. So let's come up with a couple quick examples, and then we'll wrap this section up. So we'll do an example. We'll say sets 1, 3, 5, and set 3, 5, 1 are equal. They have the same elements, the order here does not matter. Remember, sets are unordered. If we take any element from set A, it's also in set B. Any element from set B is also in set A. Therefore, those two sets are indeed equal. Another example. That doesn't look very good. We'll rewrite that. So let's say set 1, 3, 3, 3, 5, 5, 5, and set 1, 3, 5 are also equal. And this one may not be as obvious until you compare it against the definition. Once you compare it against the definition, you realize, okay, if I take any element from the first set, say we'll start with 1. So say I take element 1 here. Does it exist in set 2? Yes. How about the element 3? Does it exist over here? Yes. Element 5, does it exist over here? Yes. So every one of the elements from the first set exists in the second set. And then you can go backwards and go, okay, element 1 in the second set, that exists in the first set as well. Element 2, that's the number 3, in the second set, that exists in the first set as well. Sure, it exists multiple times, but it exists. Element number 5, the one in the third position in the second set. Sure enough, it does exist in the first set. It exists multiple times, but it exists. So those two sets are also equal.